In this next lesson, we will be talking about a different equilibrium constant called Ksp. The Sp stands for solubility product. And so we have Ksp, the solubility product constant, which is the equilibrium constant for a particular system. So it says this constant is used only for saturated solutions of slightly soluble ionic solutes. Now, technically, it doesn't have to be for a slightly soluble substance, but usually we're dealing with slightly soluble substances. But what is true is that a saturated solution represents an equilibrium system. And so for any saturated solution, we can calculate Ksp, it's called. So let's take a look at this example. Let's start off with our equilibrium equation. And the substance we're going to be looking at is lead-2 iodide. So lead-2 iodide is slightly soluble. So let's consider a saturated solution of lead-2 iodide. Now, something that's important to note here is that anytime we're doing any calculations involving Ksp, we're going to write a dissociation equation. So again, since this is an equilibrium system, we got our double arrow here. When lead-2 iodide dissolves, it doesn't dissolve very much, so we call it insoluble, but there's really no such thing as insoluble. So when you add lead-2 iodide to water, some of it will dissolve, albeit a really small amount of it. Nevertheless, it does dissolve to some extent. And when it dissolves, it dissociates into lead-2 and iodide ions. So let's write the Ksp expression for this system. So we start with not Keq or not Kc, but Ksp. And just like always, our equilibrium expression, we got concentrations of the products over concentrations of the reactants, each raised to their coefficient. So we have concentration of lead-2 times concentration of iodide squared over nothing. Notice that lead-2 iodide is a solid. Remember, no solids, no liquids ever in our equilibrium expression. So this is what it typically looks like. We have, that's why it's called solubility product of the ions concentrations in a saturated solution will give us the value of the equilibrium constant. Now, just like we did previously, the magnitude of K, in this case Ksp, tells us something about the substance. So the higher the Ksp, that means that the concentrations of the ions in the solution are greater. Well, why are the concentrations of the ions in the solution greater? Well, it must mean that more of that solid dissolved. And so that means then the higher the Ksp, the more soluble the compound is. So we'll do some comparisons of Ksps. Really, we can only compare those that have the same ratio of ions in solution. If it has a different ratio of ions in solution, then we can't just look at the Ksp to determine relative solubility. All right, so here's what we're going to do with Ksp. Lots of different calculations. One, we will calculate Ksp. So given the equilibrium concentrations of the ions in the solution, we can use those to calculate Ksp. Or we can go the other way around, where if we're given the Ksp, we can use that to calculate the solubility. Again, remember that solubility is the amount of the substance that dissolves. The amount of a substance that dissolves can be expressed either in moles per liter or grams per liter. The amount of the substance in moles that dissolves per liter of solution, that's known, by the way, as molar solubility. Or the amount of the substance in grams that can dissolve per liter of solution. We'll also look at something known as the common ion effect, and then we will be able to use Ksp to predict if a precipitate will form if you mix two solutions. So let's start off with some examples where we are calculating Ksp. Let's take a look. And here are the steps to solving these types of problems. Our first step, as I mentioned before, is to write the balanced equation for the process. Again, this is always going to be always a dissociation equation. Remember that Ksp value that has a number. There's a value associated with every substance. That number is based on that dissociation equation where you have the ions are products of that reaction or process. It's really not a reaction, it's a process. Next, from our balanced equilibrium equation, we're going to write our equilibrium constant expression. I'll just shorten it up and call it the Ksp expression. And then our last step is we're going to answer the question. Now, something that we'll see, at least in my lessons, is that I'm going to use ice tables to calculate Ksp, to help us calculate Ksp, and also to help us calculate solubility. So back to the ice tables. All right, let's look at some examples. First one, calculate the Ksp for a solution of iron 2 sulfide that has a solubility of 6.1 times 10 to the negative 10th moles per liter. All right, so let's start off with our balance equation. Be sure to include states of matter. So we have iron 2 ions and sulfide ions produced in solution. Next to that, let's write our Ksp expression. Everything is a 1-to-1 ratio, so we don't have to worry about exponents here. Make sure to include charges for those ions. It's not just Fe, it's not just S, it's Fe plus 2 and S minus 2. All right, let's set up our ice table. Now, in our ice table, we use concentrations. And since iron 2 sulfide is a solid, it has a constant concentration. So what I'm going to do is I'm going to block out this and this, but the C row under the solid is really important. So when you first put this solid in water, there are no ions. So we'll put 0 for initial concentration of Fe plus 2 and S minus 2. But how about this? When you put FeS in water, what happens to it? Well, some of it dissolves. What do we call the amount of the substance that dissolves? That is known as solubility. So though the concentration is not going to change, the amount is going to change, and we're going to indicate that here. And so what goes in the C row under the solid will be the solubility. Always, always, always. Now, something else to keep in mind is that in our balanced equation, those coefficients represent relative amounts in moles. So we always and must only plug into our ice table a molar solubility, a solubility that's given to us in moles per liter. All right, so I'm pretty sure we are given the solubility. So let's plug that in. So the amount of this, when you put it in water, is going to go down by 6.1 times 10 to the negative 10th moles per liter of solution. We have 1-to-1 ratio, so this is going to go up by 6.1 times 10 to the negative 10th, as will this. Oops, put a plus in front of that. And so in a saturated solution, the concentrations of the Fe plus 2 and the S minus 2 are both 6.1 times 10 to the negative 10th. Now that we have our equilibrium concentrations, we can plug those into our equilibrium expression and use those to calculate Ksp. I'm just going to put squared here since it's 6.1 times 10 to the negative 10th times 6.1 times 10 to the negative 10. Go ahead and pause the video and punch that up, see what you get. It looks like we get a value of 3.7 times 10 to the negative 19th. Look at that Ksp. Does that mean reactants are favored or products are favored? Remember, we talked about the magnitude of K and what that tells us about the equilibrium position. This is really, really, really small, which means this equilibrium lies very far to the left. In other words, not a lot of the substance dissolves, it remains solid, and you produce very small amounts of ions in solution. All right, it's your turn. Calculate the Ksp for a solution of manganese 2 hydroxide that has a solubility of 2.2 times 10 to the negative 5th moles per liter. Follow the steps. Start off with your balanced dissociation equation, Ksp expression, set up an ice table, and solve. Go ahead and pause the video and work on that now, please. All right, this one's a little bit different because we don't have a 1-to-1 ratio, so we need to take that into consideration. So again, our molar solubility goes here. By the way, if we're not given the solubility in moles per liter, let's say we're given it in grams per liter, just take that, convert it to moles per liter using molar mass of that substance, and then you can plug that value in. So we have a 1-to-1 ratio of manganese 2 hydroxide to manganese, so the change will be the same. But notice here we have 2 moles of hydroxide produced for every 1 mole of manganese 2. So its concentration is going to go up by twice the amount. You can write it like that, or you can just take the change in concentration of manganese 2 and multiply by 2 and plug that in there. Either way is fine. So we get these values for our equilibrium concentrations, plug those into our equilibrium expression, just plug them directly in. Don't forget about the square there. So we're going to double essentially the solubility for hydroxide in our ice table, and then we're going to square its concentration. So be careful of that. Double in the ice table, square in your KSP expression. So we get 4.3 times 10 to the negative 14th for the KSP. I didn't mention it before, but it's worth mentioning now. Just like any other equilibrium constant, KSP is unitless. It's just a number. It tells us, in this case, the degree of solubility, how much of that substance will dissolve. All right, let's go ahead and skip number 3 for now. So we'll save that for a later date and we can work that out as extra practice. Let's take a look at number 4. I think there may be a typo in your notes. So calculates the solubility, you might say of a solution of. No, we calculate solubilities for substances, ionic compounds. So just cross that off. Calculate the solubility of silver iodide. The KSP of silver iodide is, let's find that value, 1.5 times 10 to the negative 16th. So this time we're going backwards. We're given the KSP, and we're going to use that to find the solubility. And we're going to find the solubility both in moles per liter as well as grams per liter. So let's start off like we always do with our balanced dissociation equation. Lucky here, we got, again, a 1-to-1 ratio, which makes it pretty easy. Won't be the case, I'm sure, on the next example. KSP expression. And then set up our ice table. I think I forgot zeros for initial concentrations on this one. Whoops, we need a 0 there and a 0 there. Sorry about that. Just saw that. All right, so once again, what goes in the, let me ask you this way. Where in the ice table are we going to put this? Where in the ice table do we plug in the KSP? The answer is nowhere. KSP does not go in the ice table. What goes in the C row under the solid? What did we say last time? Well, we say in the C row under the solid goes the solubility. So let's plug that in. Except that's what we're trying to find. We don't know the solubility. So what are we going to use in our ice table? Sure, let's go ahead and use a variable. So if that goes down by x, these will each go up by x. And so we have our equilibrium concentrations as variables, albeit. And so we'll take those and plug them into our KSP expression. So we get x squared equals 1.5 times 10 to the negative 6. Solve for x. Go ahead and pause the video and do that now. All right, we get 1.2 times 10 to the negative 8th. Now, keep in mind that that's this value here. So that's our solubility in moles per liter. That's the molar solubility. So let's go ahead and take that molar solubility and convert it to a solubility in grams per liter. So we're starting with this, moles per liter. I'm going to write it this way. And then we want an answer that's in grams per liter. So notice that the liters is the same. So we just need to convert the moles to grams. How are we going to do that? You guessed right. We're going to use molar mass. So the molar mass of silver iodide is 235 grams per mole. Notice we want to end up with grams on top. We want moles to cancel, so that goes on the bottom. So 235 grams per mole. Mole cancels. We're left with grams per liter. Go ahead and punch that up and see what you get. So it looks like we get, I don't know if I have room here, 2.8 times 10 to the negative 6. Is that right? 2.8 times 10 to the negative 6 grams per liter. Your turn. The Ksp of magnesium hydroxide is 1.2 times 10 to the negative 11th. Calculate the solubility of this salt. All right, go ahead and set it up similar to what we did last time. Pause the video and get your answers. Let's do both solubility in moles per liter and in grams per liter, just like last time. Pause now. Here's our setup for this one. Again, we do not have 1-to-1 ratio. So magnesium will go up by X. Hydroxide's concentration will go up by 2X. So we have our equilibrium concentrations, plug them into our Ksp expression. We have X times 2X squared. Be careful. X times 2X squared is not 2X cubed. So notice this here. We have 2X in parentheses squared. So I like to call that 2X quantity squared. 2X quantity squared is 4X squared, so don't just square the X, make sure you square the 2 as well. 4X squared times X is 4X cubed. So if you have trouble solving this mathematically, first thing is divide both sides by 4, and then take the cube root of both sides, so we get just X. And we get 1.4 times 10 to the negative 4th. That's our solubility in moles per liter. Take that and convert it to a solubility in grams per liter. We get 8.2 times 10 to the negative 3rd. And then once again, I think we will save this for later. So we'll save a couple of these problems for later, as well as numbers 7 and 8. We got something a little bit different going on here. And so I think we will work through that on a future lesson or even in class. All right, that concludes this lesson. Thanks for watching.